Give two lectures. The first lecture will be on biophotonics. Actually,
switch it around.
Okay, so the first one will be on optofluidics, and then the second one will be on biophotonics. So let us welcome our speaker.
Thanks everyone. It's a pleasure to be here talking to you all. This interesting symposium meeting thing. I've never heard of it before until I was approached, but you know, it's a good idea, I think. Now, how many of you are from overseas? How many of you flew in today? Yeah, it sucks, doesn't it? Long flight, very long flight. And also, I can thank you very much for the promotion. I'm not a professor. I'm just a researcher. I'm a mere doctor before my name. Anyway, so the order initially in the program was biophotonics and optofluidics. I decided to change it around on a whim. Well, actually, it wasn't a whim. It was that I think that optofluidics is a good place to start in understanding where one can go in biophotonics, especially in the context of my research. So let's anyway begin with optofluidics. Now, I was very lucky back when I was a PhD student. I was kind of there at the beginning of this relatively new field of optofluidics, so that means the field's only been around for what? A good 5 years or so. So they're quite new in terms of things being done in scientific research. So what I'm going to do is I'm going to start with describing kind of philosophically how we arrived at this concept of optofluidics. So it wasn't just me, of course. It was my PhD supervisor at the time. We worked in optical fibre-based optofluidics. Our competitors, as it were, we're actually all very friendly. Working at a Caltech, worked on planar, so in other words, you know, light controlling structures that are made like very flat, not very long, like optical fibres. I'm going to be talking about both things today. In fact, to give you a nice sort of broad overview of the field as well. And hopefully from that overview, you can get a feel for how this, well, what I hope will be a transformative technology came to be, and also hopefully apply that in your own research. So, okay, that's enough preamble, let's get started. Optofluidics, what is it? Very simply, it's the combination of optics and fluidics. Now that's a very broad definition. The way it's come to pass is that we are combining microfluidics with microphotonics. Now, most of you won't have heard it called microphotonics, and I've called it that very specifically, and I'll get back to that in a second. Let's start with the microfluidic side. So this is a prototypical microfluidic chip, otherwise known as like a lab on a chip. You'll see there are some very sort of distinctive features. One, flat, hence the name chip. Two, there are these tiny little channels that get about on the chip. These are the fundamental structures of microfluidics. It's glorified plumbing, really. It's just very small, you know, some microns in. Excuse me, some microns in diameter. There are various bits, various, you know, squiggly bits, various joiny bits, but really, when it comes down to it, you have liquids come in, they do stuff. Liquids come out, very small scale. Microfluidics in a nutshell. Microphotonics. Light comes in, squiggly bits, does stuff, light goes out. Now you may think I'm being twee describing it this way, but I'm again doing it for a point that I'll get to eventually. Now, I mentioned earlier in the excuse me, in the kind of history of this work, that there are two kinds of photonic bases for doing this kind of stuff. And I like to think of optofluidic work based around its photonic component rather than its fluidic technology. That's just me. I was trained in photonics, that's how I think it really doesn't matter. But I'm going to use that convention in my book. So up here we have the prototypical picture of optical fibres. Light comes in this end, light comes out that end. Very easy. Down here we have something a little bit more complex. We have a photonic chip. Now what this does, and this is a very hot area of active research at the moment, takes light in, pulses in this case because we like it for communications, and communications uses pulses. We split it up into various wavelengths, we slow it down, we store it a little bit, we mix it, and then we output it. This is surprisingly difficult to do. But, as it turned out, surprisingly easy to mix with microfluidics. Hence, we get to the optofluidics. Like so. Just to ram the point home, the point of this optofluidics business is to take a microphotonic structure, be it, in this case, a tube or a fibre, integrate, remember that word, integrate, a microfluidic layer on top, bring the light field as it is controlled down here with a fluid body as it is controlled up here, and do stuff with it, to it, whatever you like. Excuse me, I've got a bit of a cold coming on, so if I break into spasms or coughing, just edit that out of it. Okay, so, giving you a little bit of a brief overview now, I'm going to talk about the principles underlying optofluidics. Can anybody tell me what those two principles are? Anybody?
Optics.
Yes! Now the gold star, you can go home. So, I'm going to start off with the microfluidics, so we're going to get into a little bit more detail there. As I said before, the canonical microfluidic structure is the microfluidic channel, and here's a whole bunch of them doing something fancy for coffee. Actually, I'll talk a little bit about this. I quite like this device. This is done at MIT, and what they're doing is using bubbles as logic. So they're using the presence or absence of a bubble to perform binary calculations. Utterly useless, slow as hell, but fun and pretty nonetheless. So, in cross-section up here, the typical kind of microfluidic channel, so cutting through one of these, is we get a little boxy type thing. Now these boxy type things, they can be rounder or they can be deformed. In terms of fluidics, it actually doesn't really matter that much. Fluid is a great averager. The scale of these things vary over several orders of magnitude, between a micron and about a millimetre. They're smaller, but that introduces what's called non-continuum effects, where you can't really talk about the fluid as an ordinary fluid. You've got to start looking at its atomic interactions without averaging out. So we won't worry about that in this presentation. When we talk about continuum mechanics, we describe our liquid with the Navier-Stokes equations. And these are found and derived very generally through considerations of conservation of momentum, conservation of mass, and conservation of energy, as all good physics equations are. This horrid-looking thing down here is the general form of the Navier-Stokes equation. On the left-hand side, we have mass transport. So we have our density, the speed at which the velocity of the fluid is changing, thus changing the mass transport through an element. A horrible, horrible little grab thing there, which is virtually impossible to compute analytically, by the way, except in a few very rare situations. And then on the right-hand side, we balance all that out with the forces occurring on and in the fluid. This tensor here is a very fluid-specific element. It describes forces being transferred through the fluid normally and tangentially. Luckily for us, the vast majority of fluids that we're going to be looking at in optofluidics behave as Newtonian liquids, more or less, which means that we can make some assumptions. And we all love assumptions because they simplify ungodly things like this. So, what we can assume from Newtonian fluid is that it's isotropic, so it behaves the same in all directions. That's cool. 2, the stress tensor, so this thing here, can be expressed as a linear function of strain. So in other words, what happens inside the fluid tangentially is linear with the force that is applied perpendicular. Now it just so happens that the vast majority of fluids found in nature behave this way, and our good friend Newton, who has done all of this already, found this to be the case experimentally, so that's cool. We also need to apply a certain boundary condition of the stress tensor by saying the resting fluid has a hydrostatic pressure. In other words, when the fluid is just sitting there, having gravity acting on it, it distributes its force evenly in all directions. This lets us somewhat simplify the Navier-Stokes equations down to this form. Still looks fairly evil, but we can take out a lot of the behaviour encompassed in this and take it down into a couple of constants, which we know and love, called the viscosity. And this really just embodies those assumptions into saying that the inertial nature of the fluid behaves this way. Excuse me. So that's not bad, but we can do better. Now, also most of the fluids found in optofluidics, and also most of the situations you find in optofluidics, occur at relatively low pressures. Relatively low meaning that we can't really compress the fluid at all. There's no supersonic flow, hopefully, in optofluidics. The automatic fluid just chips blowing up everywhere. By considering the conservation of mass inside a flowing liquid, we can arrive at this state equation. And if we assume that the density of the liquid is constant through time and space, we can come up with this lovely simplifying form. We can then substitute that back into our previous form down here, do a little bit of algebra, and we come up with a much nicer equation. So this stays kind of the same, but once you actually start solving it, some bits drop out because of this condition. Density becomes a constant, which is great. Pressure, well, pressure does what it does. And then we can just talk about one viscous term with what's called the Laplacian here of the velocity. So this is great. We now have a function form by which we can describe the vast majority of flows in our optofluidic devices. So what does all this mean? If we take our canonical optofluidic geometry up here, and we use water, because, you know, water's cool, it's everywhere. Also very handy for biological applications, which I'll get onto in the biophotonics part of my talk. We plug all this into a numerical solver, we crunch the numbers, and we find that the flow velocity profile. So hotness is speed. This is sort of spatial dimension, A and B, that you see over here. We get a very nice profile. Very boring. It's just a nice little concave shape kind of thing. We get relatively low velocities in optofluidics, given that we have, you know, these relatively small dimensions. Practically, we can't pump pressures much above a few thousand psi in the state of the art. Now, a few thousand psi sounds like a lot, will certainly blow out your car tires, but when you're talking about these sort of scales where you have these tiny little areas for that pressure to act upon, materials become rather robust, especially the ones you use for optofluidics, these polymers, these glasses, semiconductors. So there's a dimensionless number in fluid dynamics called Reynolds number. And that's defined here. Density, velocity, typical length scale, whatever that means, divided by viscosity. And it's really just a guide, it's a little bit of a rule of thumb to tell you what's more dominant in a certain fluid system. In this case, we have a Reynolds number of 1.4, which is minuscule. That means that viscous forces far outweigh inertial forces, which means that we get what's called laminar flow. It's boring. It's, well, really, I mean, like, look at some of the beautiful turbulent examples of fluid dynamics. Look at shear thinning on the wings of aircraft, beautiful, unknowable natural phenomenon. This, not so much. But it does simplify the way our systems work, which kind of is good. It means that we get no turbulence in our systems. It means you get nice, predictable laminar flow, but it also means we can't mix stuff. Now, one of the things in lab on chip, this kind of like scale or fluidics, means that you want to do chemical reactions every so often. Now, there are ways to get around this, But in these kind of constrained channels, the pressures you have available to you, the only way you can really mix things is by diffusion, which is slow and takes some time. This can be good, as I'll show you an example later. This can also be an extreme hindrance if you want to actually mix things. You just have to do it outside to allow it, and then pour it in. So that was the first bit of the microfluidics. The second bit of the microfluidics comes at what I call free surfaces. So in other words, these boundaries between gas, liquid, and a surface, or inside a channel, you can get that expressed as bubbles. Now, at small scales, at these sort of micron type diameters, surface forces are the most dominant forces you can get. There's another dimensionless number. That's something us fluid dynamics people like to do. We like defining dimensionless numbers and comparing them. It's this one, the capillary number, where you have the velocity times the viscosity divided by the, and I'll approximate it, interfacial attraction. So in other words, how much the fluid likes to grip onto whatever surface it's in. Water in a glass microcapillary, we see the capillary number is minuscule again, which means that you have several orders of magnitude greater attractive forces to a surface than you do viscous forces. Now, this is all very dependent on the surface, of course, it's all very dependent on the liquid, but this picture up here shows a little droplet of water on a lotus leaf. A lotus leaf has little hairs, some hundreds of nanometers across, and this kind of nano patterning makes the leaf very unwetting. It means water doesn't like to stick to it, and it uses this to drink. The consequence of this, when you're designing and working with optofluidic systems, and indeed microfluidic systems, is that the fluids don't always go where you want them. And once they're there, you can't always get them out. If one has, say, a silicon membrane, 100 nanometers thick, and one is trying to get fluid into it, if it doesn't want to go in, you end up just smashing the membrane using a pipette. Liquid does want to go in, then it can go in so forcefully, it will smash the membrane the other way. You can't win. Well, you can, and I'll tell you how later. Okay, so that was the microfluidics part. Let me get on to the photonics part. Now, I won't go into the photonics part in quite so much depth because there's just a lot of variety to be had in photonic structures. But I will give you the basic points to just give you an understanding of what kind of control of light we're dealing with. Photonics, described by the Maxwell's equations that we know and love. We can usually simplify those down to some kind of eigenvalue problem. So in other words, there's a set of discrete solutions describing what we call modal properties of certain structures. In optofluidics, once again, we're dealing with mostly linear isotropic materials that allow us to simplify those equations into nice kind of solvable states. However, part of the advantage of optofluidics is that you can infuse a photonic structure with lots of different chemistries that aren't really available to you as solids. And that introduces a whole bunch of curious optical properties. Gain, controllable loss, non-linearities, metallic charge, quasi-particles going through your systems. I'm not going to get too much deeper into those. That's another several hours of lectures in and of themselves, but I will mention them for some interesting applications of optofluidics. So the basic structure that we're dealing with in photonics is the waveguide. And what this is, optical fibre on the left, planar waveguide on the right, is simply regions of refractive index contrast. So here you have the core of your optical fibre, 10 microns across, a few hundreds refractive index unit contrast between the middle and the outside, and this drives our telecommunication networks. Simple little bits of glass. These are not so simple little bits of glass, and will hopefully be the basis of these photonic chips that I showed you earlier. These are made out of what's called SOI, silicon on insulator. So you have a little layer of silicon there which has grown into this kind of step-shaped thing. And the light propagates in here and in here. So this provides us with our way to control light and movement out. There are other kinds of interesting structures as well that I deal with, photonic crystals, photonic crystal fibers, where the light is constrained in here through reflection off these little bits of microstructure. As well in the plane, you can realise these photonic crystals too. And here we have a very pretty little resonator where the light just kind of sits in here. Photonic crystal structures provide a very intriguing home for optofluidics. All these little holes fill them up with stuff. You can change the optical properties in a repeatable, reversible fashion. I'll get into some of those examples later on too. So I've given you some background on the microfluidics and the the optics. Just to sum up, compare the similarities between the two. Both on the micron scale, one confines and transports fluid, one confines and transports light. Microfluidics are made out of plastics, semiconductors and glasses, just like photonic structures. They're made by lithography, which is the photo patterning of structures down at the sort of ultraviolet on 10 to nanometer scale. Apart from fibers, that is, but that's a special case. And as it turns out, because of these similarities in material, scale, and properties, it became obvious that we could combine structures, devices, and methods from these two fields to create these optofluidic devices. And here's an example of one. It kind of sums up pretty much the entire point of optofluidics. You have a waveguide that's full of liquid that's pumped in and out. This liquid is a laser dye, so it actually generates light from other wavelengths of light. The microfluidic channel forms the waveguide, constrains the pump light, and then emits this green. So, if you take nothing else away from the optofluidic lecture that I'm giving you, you are controlling light, you are controlling liquids, and you're controlling how they interact in an integrated fashion. Now, our initial ideas were to actually use this for telecommunications technology. As it turns out, not really the greatest idea in the world, in that in the fluid dynamics occurring at this scale, where they're driven thermally electronically, while they have several advantages over solid state materials, they are very, very slow to move comparatively. You can get up to a few hundred cycles a second oscillation out of a free body of fluid, but that takes design, it takes driving it fairly hard, and you just cannot compare with gigahertz oscillation that you can get in semiconductors. So it was never going to really revolutionise telecommunications technology, but sensing, however, the magic word, sensing. As it turns out, if you reverse the problem and you look at a known photonic structure and how it interacts with an unknown liquid, this kind of design, this kind of marriage of photonics and microfluidics, ideal for sensing what's going on in a fluid. And that's going to lead into my biophotonics talk a little bit later. A whole bunch of stuff you can do with optofluidics, and this is just a vague cross-section of the field. You can do all kinds of different interactions with different photonic structures. You can integrate gain. Somebody even made an optofluidic microscope where you can image live cells flowing through the device. Why you would do that, I don't know, because you can do that with an ordinary microscope, but it's cool. They've integrated metals onto the surfaces where you can get these interesting coupled charge effects, what's called plasmons. You can use very high quality resonators to do this sensing that I alluded to. And you can just go crazy and combine all kinds of fluid and photonic and material platforms to publish papers, basically. So, I'm giving you a little bit of an overview of optofluidics, how it comes together, what kind of structures you can use, and what this kind of typical scales and behaviour are. Now I'm going to launch into a whole bunch of applications from around the literature, and hopefully you'll find some of these interesting. So one of the first demonstrations of fibre-based optofluidics that I have to credit to my PhD supervisor, Ben Eagleton, down here in the 10-point type. he designed one of these, what he called grapefruit fibres. So there's a little bit of high refractive index in here, so the light is still kept in here. But you've got these holes. These holes let you access the light inside the core. And what he did was he very simply hooked up this fibre to a vacuum pump and dipped it periodically into a liquid, forming bubbles. We love bubbles. Optically, these bubbles form a mirror. And these units are in dB. So there's some orders of magnitude reflection caused by this periodic array of bubbles in this fibre. Now, of course, one of the great advantages of using a fluid is that it can move. You can compress the bubbles, can't compress the liquid, compress the bubbles, change the spacing of these bubbles, and change the wavelength of this mirror. You can do it reversibly and dynamically. Excuse me. Now, one of the other bits of sort of fluid cycling we did was with these photonic crystal fibres. I showed you a picture of this earlier. Now, down here, I have a not actually very good picture of a fibre being filled. That could, of course, be anything. Yeah, let me show you. There we go. So this picture, this dark stuff, that's the unfilled microstructure in the fibre seen from the side. And as you can see, it's just sucking up the fluid without any further ado. Now, that's another one of the sort of powerful concepts that arises from optofluidics, is that in any photonic structure with a void, you can fill it with whatever you like, provided it's a liquid, of course. You can't do that in solid fibre fabrication. So one of the things I did, let me just go back to the appropriate slide, was change the transmission properties of this fibre using a series of refractive index laws. I can do this controllably, I can do it reversibly. And there's no way you can access this kind of refractive index contrast using solid materials and fibre drawing techniques. As it turns out, the fluid moves, as I said, and I made a little squish that could be actuated. And I didn't put this in dB. Us photonics people love dB, it like smooths out all the noise at the top of these things. But I didn't because I'm an honest researcher. But as you can see, you get quite good repeatability and quite fast rise and fall times out of this body of fluid, simply moving backwards and forwards in this fibre, changing its transmission properties. Another thing that was done with this at by Yariv, a quintessential optoelectronics researcher at UC, University of California, San Diego, I believe. Now, what he did was he not only filled up these fibres, but selectively filled them up. So, in other words, filled up the hollow core rather than the sort of cladding material around the outside, and filled that up with a UV curable photopolymer. So, in other words, something that goes hard when you shine UV light on it. And once again, this way he made a now permanent kind of adjustment to the refractive index profile of this fibre, changing its dispersion properties, changing its guiding properties. Once again, not really reversible in this case, but can't really do that with any kind of solid fabrication technology related to glasses anyway. Now, people love this optofluidics thing for sensing. One of the earliest sensing demonstrations was using one of these, what we call imaging fibres. They look like the photonic crystal fibres, except they're bigger. So you don't get this, what we call coherent diffraction effect, where the light is guided in the middle. Each one of these little holes, which are about 100 microns across, a few hundred microns apart, act as individual cores of the fibre. So if you were to point this at, say, I don't know, random light source, you would get a representation of random light source at the other end of the fibre. What this guy did was he, what we call functionalised the surface. So he actually used surface chemistry to attach biomolecules to the outside of these cores, probed them, looked at the image that came back, and could tell which of them had been bonded to during the course of an assay. This is really one of the first times that anybody had use these for biosensing with an active chemical medium on the outside. That's a very sort of very powerful idea. This is a surface enhanced Raman fibre. So it's really yet another one of these little holy fibres. Again, it's an imaging fibre, so relatively large kind of individual cores that run along it. And what they've done is coated it with metal. Now, what metal does to the Raman signature of the molecule, so the re-emission of light when you probe it, is that it enhances this re-emission by something like 15 orders of magnitude. And what this Raman signal can tell you is structure, identity of the molecules. They're used for fundamental investigations in organic chemistry. So to get this kind of increase in analytical signal is something fairly major out of such a simple device too. So I'll give you a little flavour of the fibre optofluidics. I'll move on to the planar optofluidics now. So as I mentioned, these planar photonic crystals now, so they're made in a little sandwich, a little layer of silicon, about 200 nanometers thick, hollow underneath, hollow straight through, so they form a great home for fluids. You can also take out rows of holes and form waveguides, resonators, homes for light. So it would appear that these photonic crystals are really quite ideal for doing optofluidics because they provide a really nice home for the light and a really nice home for the flickers. Of course, there are an infinite number of practical challenges in doing this, but theoretically it's nice. One of the first demonstrations of these tuned photonic crystal waveguides was done at Caltech a few years ago. And what this guy did was underneath this photonic crystal layer is a microfluidic channel. Not very wide, it's about spans a couple of periods of the photonic crystal. And he could simply flow through different liquids and modulate whether or not this guided light. And he published this in DB, so he's not on it. And you can see there's still a whole bunch of squills on either side, and it's still slow as all optofluidic technologies are. This is back in the good old days when we thought we could use this for communication. But the point being, he achieved a completely reversible, stable modulation of the transmission of the photonic crystal waveguide, which nobody had ever really done before. So that's just sort of one row of holes that's targeted by a fairly crude, relatively speaking now, channel. What we're doing here, so plug this in here, is we've developed a method to actually individually address the holes in this photonic crystal, so we can fill individual voids with whatever fluid we choose. What this does is it changes the dispersion of this waveguide. So in other words, how the waveguide, the speed at which this waveguide guides different wavelengths of light. And this is important for pulse propagation, especially a certain kind of pulse propagation called slow light. Most waveguides have this kind of dispersion profile. It's just the way things are. You get this kind of dispersion profile with a little hump in it. You can slow a pulse of light down so that the phase velocity, the state-of-the-art slow light phase velocity is something like a few hundred meters a second, which compared to the natural speed of light, ridiculous. So again, why don't we do this? Why don't we do this lithographically? Well, optofluidics provides us with several advantages. One, completely reversible. We can wash out our samples so poor little us don't have to use hundreds of thousands of dollars worth of lithography time. We have this range of refractive indices, which is great. It means we can tune the refractive index very specifically to the nature of this waveguide to optimize this dispersion profile. Excuse me. And yeah, we can achieve these kind of dispersion profiles much more easily than you can with standard lithographic design. And you can also use it for sensing. This is one of the surface and chemistry modulated devices that I was alluding to earlier. What these people have done is just taken a planar photonic crystal resonator, which you can't see up there, calculated the modal, so you know you get really nicely confined light in this little hole, and they have chemically attached bovine serum albumin, which is just something found in cows, as the name would suggest. And this has a very specific binding onto another kind of protein. And they detected these binding events through the shift in wavelength of the resonator. That's fairly extraordinary in my mind, that you can actually pick up some tens of thousands of molecules worth of binding events, then wash them away with this kind of accuracy, repeatability. So yeah, everything else is just a different microfluidic configurations, different photonic configurations. This is a single beam interferometer, and the way we designed this was we've got two optical fibres and put a square capillary in the middle. Now we use squares simply because we didn't want the light diffracting off a round thing. We just flowed some fluid in there. The fluid had the same refractive index as the background glass, and depending on where in the beam the meniscus, or the boundary of the fluid was, we could control the depth and wavelength of this resonance. That I thought was quite a nice kind of demonstration, provides a real kind of feel for the advantages that optofluidics can give you. Also made a little refractometer, so once again just a couple of fibres. There's gratings written into these fibres so they act as a mirror. A pair of mirrors becomes a resonator. Shift in wavelength of the resonator tells you what's going on inside this microfluidic channel, which you also cannot see here. The point of this kind of design is what I like to call semi-planar. So you take the best of both worlds. You take the high quality optics available through standard telecommunications hardware and techniques, and you very easily interface it with this kind of microfluidic technology, which is where the planar fabrication comes in. This stuff is pretty cool. This is a two-liquid waveguide. So remember how I mentioned earlier that mixing in microfluidics is diffusion driven, so it's very slow. It takes a relatively long length of flow to have this miscibility and sort of averaging out of chemical composition. What these guys did was they had two flows that came together. One on the outside forming a waveguide cladding, one on the inside forming a waveguide core, and all they did, the same liquid, or water, had different concentrations of calcium chloride in it. The refractive index contrast between these two liquids was enough to guide light. And because fluids move, they apply different pressures, which means that on this output here, you could shift the core of this waveguide to whatever output you wanted and have that light up appropriately. Another thing that optofluidics is surprisingly good for is making lasers. Now, 20 years ago, the technology du jour for the lasers was the dye laser. Great big get-out resonators with these gain media that you had to continually pump and recycle, highly carcinogenic. You had to use great volumes of them. It was a real pain, frankly. In this work, they made a little mirror by simply creating this kind of pattern. This is called a distributed feedback rating. So it means that the reflections of each one of these little ridges at the appropriate wavelength add up coherently, so it gets some intensity. And then you just flow dye over it in a little microfluidic channel. You pump it from the top, so the light that induces the laser is focused from out of the plane onto the chip, and then it blazes. As it turns out, the microcirculation of the fluids in these kind of devices means that you don't have to worry about recirculating the dye. This is somewhat surprising because one would have thought that there wasn't much flow in these microfluidics, but once you start heating them up, once you start getting convection going, even on a small scale, that's enough to rejuvenate the gain medium. One can also do non-specific binding optofluidic sensing. So in other words, you can have a resonator that doesn't have any chemicals attached to the surface, and you can still pick up changes in composition just through refractive index difference. And perhaps one of the most successful demonstrations of this is this chip up here that you also cannot see. My God, I hate projectors sometimes. You have your microfluidics coming in, and you can just vaguely see a pair of rings. Can you see those? Sort of lit up green. No? Well, visualise. Visualise a pair of rings up here, and they're optically probed with waveguides that you also have to visualise going down the side. If you make these rings out of the right material with a high enough quality, so in other words, the best roundness, the best smoothness you can possibly get from your fabrication process, you can pick up ridiculously small external changes in the fluid that surrounds these resonators. And the best demonstration to date is this one, where the researchers picked up a 3 parts per million change between deuterated water and water. So that's like proton, like outstanding. So yeah, that sort of brings me to the end of my end of this particular talk. Thank you for your attention, and I hope that you have some understanding of optofluidics now, and more importantly, how two fairly disparate technologies can be brought together for, well, apart from publishing some papers, hopefully for some good. Thank you.